So welcome everyone. This is the Quant University Summer School Series. My name is Sri Krishnamurthy and I'm going to be the host of the show. Today we are very excited to have Navdeep Gill from H2O.ai, who leads responsible AI efforts there. And he's going to be talking about one of the most discussed, a topic which is very much in discussion in today's day and age, which is secure machine learning. As machine learning goes into production and a lot of practical and interesting challenges are evolving in the industry, it's always interesting to see, how people actually think about the whole context of deployment and monitoring, and also looking at like what are things which could potentially go wrong when you deploy these models in production. And security is one important theme. Privacy is another important theme. When you think about making your models available and having other companies or other people having access to these models, what are the various aspects you got to think about? So Navdeep and Patrick Hall and others, they have written a very nice book, and the book is also shared on the website. And a segment of this is this topic of secure machine learning. And when Navdeep and we spoke a few weeks ago on various themes, I thought this would be very appropriate for today's session. As you all know, Quant University has been hosting these sessions for the past year or so, and this is the 47th session in the series. We have hosted eminent speakers who are in the industry, academia, who are practitioners themselves and are experiencing these challenges on a day-to-day basis. We are also thinking about how this whole field is evolving as we try to bring in discipline into this whole area. And in that realm, my personal passion is to not only appreciate the theoretical aspects of it, but also looking at what are the various challenges we'll have to deal with when we are pragmatically applying various machine learning and AI techniques in your day-to-day work. So I hope these sessions are helpful, and it helps you ask questions and think about the various things which you may not have thought about when you are thinking about machine learning. So let me kind of take a minute to share a couple of updates on the Quant University side, and we will hand over the stage to Navdeep. So as you all know, we are Quant University. We're based out of Boston, and I think location is going to start becoming important now that we are no longer restricted to the online world. So we do a lot of programming in the Boston area, New York, in the East Coast area, but we also do a lot of advisory work focusing on the intersection of data science, machine learning, and finance. We do a lot of educational programs, partnering with organizations like Premier. And in that realm, we are hosting a summer school wherein we are offering various courses in machine learning and AI for people who want to ramp up on these skills, primarily in the financial services context. On the other hand, we are also looking at themes to risk management when you're adopting machine learning models within the industry. And in that area, we are building out courses in the context of stress scenario testing, algorithmic auditing, and model risk management. And as you all know, we have been doing a lot of work in making these tools available through the Q Sandbox, and many people who take these courses also get an opportunity to use the Q Sandbox. But we're trying to build out an enterprise system which will enable you to try out various aspects of model building, testing, tracking, and also a platform to enable algorithmic audits and assessments of various kinds of models. So if anybody's interested in discussing more in those areas, please shoot me a note and we can set up some time. Today, we will focus on secure machine learning. And as many of you know, Navdeep has been a pioneer in doing various projects in the context of machine learning and AI. I came to know about Navdeep's work when I was kind of reading and researching some of the materials in the context of explainable machine learning. And Patrick Hall and Navdeep, and when they were working at H2O, they had written about many articles and variety publications, which I was very much appreciative of because they've been shared openly and freely. But also Navdeep has interests in various aspects, as we'll discuss in the context of secure machine learning. And Navdeep is no stranger to machine learning, so he has both pragmatic experience, but also from an education perspective. He has studied at California State University and University of California, and done research in various areas. So welcome, Navdeep, to today's session.
Yes, thanks for having me. It's a pleasure to be here. So I can basically jump right into the presentation, and we can sort of discuss things after that.
Absolutely. So you're the co-host now, and you can present.
Yeah. So I'm assuming everyone can see my screen?
Yes, we can see your screen. Yeah.
Perfect. Yeah, so today's topic, I'll be going over secure machine learning. People have discussed this for quite some time in various aspects. And I hope from this presentation, I can compile together some, I guess, different types of attacks and different types of methods I've sort of read about, and Patrick Hall and I have sort of written about in the past, just to give you a sense of, what can happen with sort of insecure machine learning, or machine learning where this aspect is not taken into account. So we can go to the first slide. So yeah, the contents, I'll sort of go over, why someone would want to take part in secure machine learning, or not secure machine learning, why someone would want to hack a machine learning model. I'll go over some attacks that people can do, some general concerns. I'll try to pose some solutions, and then we'll just summarize everything at the end. So here we can go over some of the reasons to attack a machine learning model. So as you guys can probably guess, a lot of the times this has to do with gaining, beneficial outcomes for the hacker or a group of hackers. So the main thing is to sort of get the machine learning model to work for you so you can get the outcome that you desire. So I think that's one of the biggest reasons. Other reasons could be, they just want to infiltrate corporate entities. So, there's, you can think of, when it comes to hackers, there's probably two types. There's the type of hacker that sort of works at a company that basically does security checks or security audits. And they will do something like this for machine learning models, most likely. And then there's type of malicious hackers, usually not in a company, sometimes they are, but they are involved basically in malicious behavior, like I said, trying to gain an upper hand with whatever outcomes they're interested in, or just trying to disrupt some industry that they don't find attractive or find useful, or feel like it doesn't work for their favor or cause. And sort of the last bullet point is they want to gain some type of intellectual property. This could be anywhere because, like I said, do beneficial outcomes, or they can use it for themselves if they have their own machine learning venture. So there's various ways and various reasons people are interested in hacking machine learning models, or hacking any system in general. And these are sort of, I think, these are sort of the main three that I think are specific to attacking machine learning models. So now we can jump right into the first type of attack that someone can take part in. So this is called the data poisoning attack. This is essentially when a hacker sort of obtains access to data. This could be, the training data, validation, test. And what they do is they alter it before model training. And the reason to alter it is because they can change the data in such a way that it favors a certain group of people or a single individual, or it can cause erroneous results that they want to expose. So that's sort of the main reason behind data poisoning attacks. Now, how this can play out is sort of twofold. You can be in a small company, and usually in small companies, a lot of times, various people have access to different components of the machine learning pipeline due to the nature of it being a small company. So there could be someone who's allowed access to training data and model training and model deployment. They're sort of just able to get into all of these systems. So you can imagine if there's an inside hacker, they have various avenues to sort of take part in this hacking exercise. And so that's one component. Another component is you could be at a massive company, and then sort of these hackers are working in secret to either gain permissions, to manipulate training data. So you can imagine gaining permissions into some ETL processes, which are usually well guarded, but there could be a way to sort of get into these systems. They get into systems that involve training models. This can be anywhere from, at a data scientist's desk, or in some cloud instance, or on-prem type instance, or they get into systems that deploy models. So this is when you get into sort of the realm of machine learning engineers and software engineers. They can sort of get into those systems as well by working with others who are involved in those systems. So this is sort of a covert activity, and it's sort of orchestrated amongst several people. So you can see the minor differences there is that a small company, technically, you can think one person can cause some damage, essentially, if they have access. And at a massive company, it could be a group of people. I know this sounds sort of terrifying that this can happen from an internal company standpoint of view, but we have to assume that it is possible. If it's possible for other aspects of cybersecurity, there's no reason why it wouldn't be possible for machine learning models or deploying machine learning models.
So Navdeep, can we just kind of pause here for a second? So how would this? How is this different from especially the small company example? It's just traditional cybersecurity, right? Does it have to be specific with machine learning? Because someone who has insider access, that's always a cautionary thing you'll have to take care of, right? So someone has access to a lot of sensitive information, then the risk is always there. Now, anything specific with respect to the machine learning context which you need to be aware of?
Yeah, I think with the machine learning context, yes, initially this is sort of a cybersecurity type problem when it comes to just the access situation. I think the main difference is how to remediate something like this. So what methods do you take part in to remediate someone taking hold of your training or validation? It's not really just the fact that they get it, they're going to do something with it. And then you have to capture what they did. And that involves certain, aspects that are related to data science, which I will kind of point out later. There's certain methodologies that are probably specific to data science instead of specific to cybersecurity. And you're sort of combining the two. So you're taking these data science methods with this aspect of cybersecurity, and you're trying to uncover a potential attack. So that's how you're sort of keeping track of everything. So it's kind of a combination of the two. But initially, yes, this is a cybersecurity type topic. There's data everywhere. They want to protect it. So that's one aspect. The other aspect is how to remediate something like this. So from a data science standpoint, there are specific methods that I can go over later, which sort of differentiate the two.
Well, thank you.
And then here is sort of just a pictorial that you can think about. So essentially, it's basically the same thing. We have this hacker who's sort of changing the original training data to favor them. So in this case, you see this is sort of a default data set, and you see initially this row of data has been denied, and then they change it to not denied because you're predicting the probability of default. So this is sort of a simple example where someone just changed the training data, then the model is training on this data, and then it sort of learns this rule. Now, obviously, it won't just be a single row. This person might manipulate several to the point that they can change some outcome. But the concept still remains the same. The logic still remains the same. So now here's some defenses. So this is going back to the cybersecurity versus the data science security aspect. So one method you can do is you can look at sort of disparate impact analysis. So this is a way of looking at differences in groups. A lot of times this is used for fairness. So you're looking at fairness metrics, but there's nothing that stops you from using it for other metrics as well. So you can look at, how are the predictions ranging between different groups of people, and do these ranges make sense given your domain knowledge and the things of that nature. So if you sort of go back to this previous one, you can see that they have they're delinquent by 4 months. Their FICO score is not the best, but they still are not going to get denied. And then if you look at this across various rows, like I mentioned, this hacker is not going to do it for one row. That's not a good hack. They're going to try to manipulate it in such a way that various similar rows cause the machine learning model to learn this logic, and then the outcomes start happening for them. So you can imagine if you did disparate impact analysis and you looked at the predictions across these variables, you would see most likely some odd behavior or something you wouldn't expect, which will of course cause you to dig deeper into the process itself. Because you could imagine in a data science pipeline, everything starts from the ETL process. So you would think, when did this person change the data? If they changed it when the training data was being made, there's still an ETL side that kind of has the actual information. So this is basically the first step, I think, or one of the first steps you can do. It's pretty straightforward, and it's sort of and some detective work on your part to make sure there's nothing off. And this is not something I think specific to just security. I think it's specific to good data science practices. You want to make sure that the patterns that are in the data make sense before you actually start making a machine learning model. Or, you make a machine learning model and then you vet it before you deploy it. So it's not just a matter of looking at accuracy. You want to make sure, is it learning the right things?
Well, pragmatically, do we draw a line between data quality reviews and security or potential hacking reviews? How would we operationalize it? Is there going to be a different department which will potentially look at this analysis, or would it be a part of your ETL pipeline itself? You're going to make sure that it's not a data. I mean, it could be a benign data quality issue, right? Because it could just be the way we source it. There may be a lot of gray area, which could result in these edge cases.
I think eventually, initially it could just be a data quality issue. So it could just be, as the data is coming in, something goes wrong with the ETL process. But that's not to say someone interferes with the ETL process as well. That's always possible. Also, when the ETL process is happening, a lot of things that are mentioned for security is sort of this documentation aspect. You want to document what you're seeing. So if an ETL process comes in, and let's say the engineer or whoever's working on it, or the group of people working on it, document what they saw in the data before it got into the hands of anyone else, then you have a sort of source of truth about, what was extracted, how it looks, the cardinality of categoricals, the min and max of numericals, the number of duplicates, et cetera. All of that stuff is documented, which allows sort of a data scientist or analyst to kind of look back and compare and contrast what they're seeing. So that's sort of the one way that you would operationalize it, just from an ETL standpoint. And then another way is sort of if you have the luxury of having sort of security engineers, they can learn this, I think, pretty easily and kind of operationalize it themselves in their own pipelines, or whatever that may be. But I think Lisa's first one, disparate impact analysis, I think this is pretty straightforward for a data scientist to do just at their desk. And then, sort of once again, they go back to documenting what they see, they compare and contrast with what the ETL process showed, and there might be some discrepancies. And now, if there's discrepancies at that point, it could be due to error. So it could be due to someone messed with the data incorrectly, and then that caused issues, or it could be something else, which is from a security standpoint, data poisoning or something like that.
Oh, thank you.
Yes, and the next one is sort of fair or private models. Now, the idea here is you're basically trying to prevent the model from being discriminatory to protected groups, or whatever groups you deem protected. So what this will do is this will essentially help you with a specific type of data poisoning attack, and that's when it comes to messing with sensitive variables, or adding variables that are sort of correlated significantly, or manipulating variables so they're correlated. So these type of models will sort of ensure that there is, I guess, no bias introduced or anything like that. And this can help prevent a discriminatory data poisoning attack. I won't go into too much detail into the models themselves, but I do have references. There's things like learning fair representations, and there's private aggregation of teacher ensembles. Essentially, what all these are trying to do is ensure privacy, and they're trying to ensure fairness. This is sort of one way to do it. I should mention that this is not the end all be all. This is still going to be a combination of some more exploratory analysis and comparing and contrasting to other models that you have built. But it is a good first step, at least from a security standpoint. Now, another aspect is reject on negative impact analysis. And then this is basically a technique that removes data from the training set that sort of decreases prediction accuracy. The main idea here is that it's sort of causing you, first you're exploring why the decrease is happening. And the decrease could be due to, say, odd results with the row, or the row looks very odd, or the set of rows look very odd. And then this can allow you to sort of explore further and sort of see why this is happening. And there's a reference here. There's actually a good article called "The Security of Machine Learning" that sort of goes over a lot of these topics and other topics that I haven't covered in much more detail. And the next one is straightforward residual analysis that has been around for many, many years. And basically what you're looking for is sort of large deviances in the residuals in the positive case and the negative case. And what you're trying to do is, once you find these large deviances, you're going to drill down and see why this is happening. And you might uncover some odd behavior in the data itself. And like I mentioned, this is a pretty straightforward analysis. It's been around, I believe, maybe since the 40s, maybe 50s, and it's always been reliable. I don't think it's just stuck to statistics itself. It's something you can use anytime any type of model is built. The last one is the sort of what we call self-reflection. You're sort of you're scoring your models on employees, consultants, and contractors and seeing if there's anything anomalous, because these could be people who manipulated the data itself. Now, this is, I think it's kind of controversial because, you're sort of putting models on your employees and, things like that. But it is possible, I think, if sort of understood amongst the organization or understood amongst your team, this is a way to sort of figure out any anomalous behavior. And if you notice some employees or contractors, et cetera, are highly favored, significantly favored, then that's something you should be alarmed about. A lot of times that shouldn't be the case. At least for a good machine learning model, it shouldn't be sort of driven by one or two things, and then it's just making the prediction. That's not good in general, which is something to consider as well. So now we went over data posing attacks.
So, in your experience, in these techniques, are they usually done at a post-mortem level, or is it to be done proactively even before the model is deployed into production, or kind of goes into this whole online, regular monitoring aspect wherein you are constantly keeping track of all these aspects whenever you are, building out your life cycle?
Yeah, I think this is usually pre-model building. You can do it. So like I mentioned with, comparing and contrasting how the data has evolved over time. And also post-model building, where you're sort of looking at predictions across, like disparate impact analysis or the reject on negative or anything like that. That's sort of post-model. So you want to capture all this before you deploy it, because once you deploy it, it's going to be sort of hard to backtrack to the data poisoning. It might even be too late. Your model's already scored on various individuals or groups or observations. So at that point, it might be too late. However, if you have a system in place where you can sort of pull that model and use another model that you feel that hasn't been susceptible to this type of attack, then you might be okay. So that's where, that's not covered here, but we do talk about sort of the MLOps process where you sort of have these backup models, benchmark models, et cetera. I think that's one way to maybe capture this once the model is deployed, is basically to have a backup plan and then investigate the model you initially deployed to see what the problem is, to capture anything anomalous or something that doesn't make sense to your team or to you yourself. So that's sort of one way that can kind of span the entire life cycle. Obviously, you want to capture this before you even deploy the model. Yeah. So the next type of attack is called backdoors and watermarks. And essentially what this involves is, there's people in your organization that sort of change your production scoring code. It could be before or during deployment, and they sort of add this backdoor that can be exploited with what we call watermark data. So this is a common, this is a common concept in cybersecurity, but this is a sort of a unique set of information that will cause a desired response. So this could be a type of information that you're not initially aware of because they inject it, once you've sort of deployed or you're close to pre-deployment. And then once that's injected, they know the specific, I guess you can say, rules or set of information that they can sort of throw at your machine learning model once in production and then get the outcome they desire. So here you can see this in this pictorial, an attacker basically added this extra variable that they've sort of manipulated, saying, if it's greater than or equal to 0, deny. If it's less than 0, approve. And they sort of added this after looking at the FICO score, which initially led to deny in this sort of tree. So essentially someone just injected some logic that wasn't originally there. And then now the model will respond to this injected logic very easily, and they can get the outcome that they want basically every single time, because they know they added just this simple Boolean at the end. So this is one way, backdoors and watermarks can essentially work. And you can see they took the original model, they altered it, and that's basically the simple concept there. Now, some defenses, you can do sort of anomaly detection to sort of see if there's any type of, obvious predictions that are sort of favoring one person over the other. And then once you capture this anomalous behavior, you can investigate it further. The next one is sort of data integrity constraints. So, you shouldn't, or you should try to figure out what type of combinations of variables or values for variables are sort of unrealistic. And you should sort of document this, obviously. And then you should inject this into your production scoring to ensure that when data comes in, the inputs make sense. And if the inputs don't make sense, it should sort of, return that back into the production system and sort of guide it into what should happen. Once again, you can still do, for the next bullet point, you can still do disparate impact analysis. So you can sort of see how the predictions are changing once again, given some type of, or given some instances of data. So in this case, for example, you see that the altered model, it basically looked at initially, this is a pretty simple model, but what it basically said is, if FICO is less than 700, I'm going to deny. But if all of a sudden, people who have low FICO scores are actually getting approved, that would be discovered in disparate impact analysis just by looking at predictions alone across this variable. So you can imagine, just bucket up the FICO scores and then do like a group by, and then you would see some odd information. And then that will allow you to sort of uncover this potential backdoor or watermark.
One of the challenges I always have with anomaly detection is defining what's normal, right? Mm-hmm. As things to constantly evolve. What was normal a few days ago may not be normal now. Right? Yeah. So, so the defense mechanism also needs to constantly evolve at that point.
Yes. And yes.
How do we make it happen in the context of not having like rigid rules which will potentially raise red flags? Is it going to be a human in the loop kind of a situation wherein or even uncertainty quantification metrics wherein as you start becoming more and more uncertain about your outputs, you want to intervene? How would we, and the reason why I'm asking this is the way I'm seeing the machine learning pipeline, there's a lot of emphasis in the modeling world on neural networks, very complicated models. I mean, you're not able to like individually decide even the whole explainability debate, right? Like, what attributes are actually resulting in your outcomes. And now we are putting in a set of guardrails afterwards, potentially looking at what's abnormal and trying to take actions based on those. So the complexity layers are kind of growing. So should this be a part of your modeling infrastructure itself, or the guardrails and the watermarks come after that?
Yeah. I think there should definitely be a part of the model production or the model building system as well, specifically with anomaly detection. Yes, this concept will change across use cases. There'll be different anomalies and, I guess, different data sets. So then you have a different set of outcomes, and you have different values for variables, different type of production scoring code. So this type of thing will change from case to case, which is why a human in the loop is usually necessary for many of these things. A human in the loop will be necessary. Even with sort of security analysts and cybersecurity and things, they're constantly monitoring things to ensure that nothing odd happens. Usually the way I think that works is, of course, an anomaly has to be detected, but once it's detected, it has to be investigated further. So I think this is the same. Once the machine learning model is deployed, it is monitored by an engineer, machine learning engineer, usually, and then they will have some mechanism in place to ensure that the scores aren't sort of, all over the place, or very weighted towards one side versus the other. And they also want to ensure, sort of the data integrity as well. The data that's coming in, does it make sense? That's sort of one way, I think, where a human in the loop is always the case. Even with these sort of, you would think these sort of mechanized type of things, a human still has to investigate after some result is figured out.
Oh, thank you.
And the last thing I have here is sort of version control, which is probably one of the most powerful things when it comes to this. This will just keep track of your production scoring code. So whatever you're going to use in deployment, this will keep track of how that logic or how that mechanism has evolved over time. Now you could imagine if you were keeping track of everything, you have a history of what happened. And this will most likely make it difficult for someone to add a watermark. At least they'll cover a big chunk of that. That's not to say those other steps are not necessary, but this step is pretty common in software. And I don't see why anyone would not do this. So I think it would definitely help in this specific case. So now we'll go on to the next type of attack, which is called a surrogate model inversion attack. Now, what this is basically, if there's not enough security at your model API, hackers can sort of simulate data, submit it to your API, get back a prediction. Once they have their prediction, what they have is the data that they inputted with the prediction. So you basically have a row of data, and then they can keep doing this until they end up with a data set. And then they can train a model where the inputs are what they sent to the API and the outputs are these predictions. So it's a, surrogate model is a model of a model. Most of the time with machine learning models, you're trying to get a sense of, reality based off of the data that's been given to you. What a surrogate model is doing is trying to get the sense of reality from the model. What is the model thinking? In this case, a hacker can definitely do this if you don't have enough security, and they can figure out what your model's logic is. And then what this will do is most likely it'll expose some proprietary business logic. So you can think of it as model stealing. It can reveal sensitive information based off of your training data. It's usually the first stage of a membership inference attack, which I will go over later. And it can also be a sort of this exercise for adversarial attacks, which I will go over as well. But this concept will come up again a couple more times in this presentation. So see here, it's basically a pictorial once again. An attacker simulates data, sends it to the API, the model gives a prediction, and then you see it's like a loop. So the attacker keeps doing this until they feel they have enough data to sort of build something. And then you can see on the right there, they sort of built this model. You can say it's a tree-based model, or and then they basically figured out some logic. And now they have a model that simulates the model that a company deployed. For, in this case, you can say it's a bank that deployed a model to figure out probability of denial, which will dictate, the response they will give in terms of accepting them as a customer, not accepting them, or accepting them on certain terms, et cetera, et cetera. Now this hacker can figure out all that information. So there's a few things you can do. There's authentication. So you just want to make sure that the amount of times your API is being hit is acceptable. So you can see this in sort of a lot of things. It's sort of like a DDoS type of attack. So if someone keeps hitting an API, a lot of times online entities will feel that's sort of odd. So they will shut down that service to whoever that person is. You've probably seen this if you try to use an open source API to say Twitter or Facebook or anything. And then if you get the key to access the API, but you do too many hits, eventually you'll be stopped. And then there'll be some time delay until you can do it again. So that's the way to do it here, is you have to have some type of authentication. Another thing is you can have sort of these defensive watermarks. So essentially what you're trying to do, so initially I explained a watermark in sort of the hacker's point of view, where they're adding information internally to kind of dictate what the outcome will be. In this case, what's happening is it's sort of the same concept. You're sort of adding subtle information to your model's predictions. And what this will help is sort of in forensic analysis. So what would happen is, basically the forensic analysis is to see if the model was hacked or stolen. So that's what you're trying to achieve with this type of analysis. And then you can think of this watermark as something similar to a physical watermark that you might see on some currency to help catch, fake currency versus real currency, which you would commonly see in the, in sort of the US with like the latest bills that we've been giving out to people. So that's one way to do it. And another concept is throttling. So this is when you sort of consider slowing down your prediction response times once you detect some anomalous behavior. The idea here is, give yourself or your team some time to investigate, before things go haywire, essentially. This is not to say you'll stop bad things from happening, but you'll just slow down the process enough that you won't incur too much damage, if you want to think of it that way. You're just trying to sort of control everything to a certain degree as much as you can before things go terribly wrong. The last one here is sort of a called the white hat surrogate model. So basically what this is internally you do a hacking exercise and you want to see what an attacker could potentially learn about your public models. And then you can come up with types of protections against it. So this could be like defensive watermarks. You can try to figure out maybe if there's a throttling mechanism, you can make the authentication a lot more strict, or you can, work with security engineers to figure out how we can ensure that this authentication cannot be manipulated or sort of hacked into. So, this is sort of a common thing. You can think about the white hat surrogate models in cybersecurity. They have bug bounties. A lot of companies would do that, and they have competitions actually about bug bounties where you're trying to find bugs within some type of system they have. And some companies do this with their security engineers. They want to make sure that they're protected in all aspects, and the security engineers, of course, know how someone can get into a system, and they will basically try it internally. So there's no malicious, ideas here. It's basically an exercise to figure out what can happen. And then once you know what can happen, you can try to figure out a potential solution. So now we can go on to the next type of attack, which I mentioned is where the first stage is a surrogate model inversion attack. So this is called the membership inference attack. It's a two-stage attack. So the first stage is usually you want to do the surrogate model inversion, which I mentioned earlier. So just basically stealing the model. Then you want to train a second model to discriminate between rows of data that are in and not in the first level surrogate training data. And then once you know that, simply knowing if a person or an observation is in or out of the training data set, this can, of course, violate privacy. And if you do this, to the fullest extent, you can sort of rebuild the sensitive training data just by figuring out what rows of data are in the model or not, or in the surrogate model or not. So this is sort of the pictorial again. So the attack begins with a trained surrogate model, so the model stealing, and then the attacker would augment the surrogate's training data with new rows that are not in the original training data and score them with the surrogate model. And then the attacker trains a second level surrogate model that can discriminate between the rows that are in your training data and not in your training data. So then they can start figuring out how to rebuild this training data set, which is, so it's not just enough to steal the model itself. They're sort of stealing or figuring out your data set, which is, of course, a big problem. I mean, when companies build models, et cetera, they're not giving the data set out to the world. There's a reason they protect it, whether it be privacy or it's just, it's your data. You took the time to collect this data. The models being built on this data are for your company. You're most likely to make profits and to work out use cases that you find, useful. So this is sort of doing the full spectrum, stealing the model and getting the training data, which is, once again, a very horrible situation to be in. So essentially, the defenses are still back to slide 12. So these concepts basically apply to a membership inference attack. And then you should also monitor your training data. So basically, you want to monitor the scoring queue for data that closely resembles any individual used to train your model. So real-time scoring of the rows that are very similar, identical using training, validation, or testing, they should be recorded and investigated. So if you're basically seeing rows of data that are very close to the rows that were trained in your model, that's sort of, that can be considered somewhat odd, especially if they're really close. That's basically saying that there's a person out there who's basically the same as the person in your training data set, which could be possible, but if it happens enough times, then it becomes odd. So it's not just, once, it's odd, it's, when it happens a decent amount of times. And then what you're doing, once again, is you're documenting when this information comes in. So you basically end up with a history of what you're seeing, and then you can do some type of analysis to figure out if there's really a problem or if there's really something malicious going on. And then I think this is second to last one. So this is called adversarial attacks. So once again, you might have a lack of security in your model API or other model endpoints. And then what attackers would do is they would simulate data, submit it, receive prediction, and basically learn by trial and error the business logic, and then also how to game your model itself. So basically, once they're learning all of this, they're basically learning logic, and they're basically seeing, what logic gives me the positive outcome, what logic gives me the negative outcome, whatever the negative outcome would be. And then they can also evolve over time. Obviously with trial and error, you're only going to get better and better and better. These adversarial attacks will get better and better and better. And then someone would be able to get, any type of outcome they desire from this type of attack. So once again, this is sort of this, a pictorial again. You see an attacker systematically just altering data until they receive the outcome they want. So if the API is basically telling you you're going to be denied for something, the attacker would keep simulating until they're not denied. And then they've learned what combination of features or input variables are needed to get the outcome they desire. And once again, if you in the next slide, you'll see this once again, but the lack of authentication could easily make this happen. It's if there's no authentication, it's not going to stop you. So this is something to consider when it comes to authentication. This is one other aspect that can be guarded here.
Is there an assumption in here that the model parameters or the model itself is not transparent and not available for understanding? And the attacker is trying to reverse engineer the model parameters of the model itself?
Sorry, could you say that again? Maybe I didn't.
Yeah. So here, is there an assumption here that the model is not transparent and the model parameters are not evident? So the attacker is trying to reverse engineer and trying to understand the model parameters and the model itself. Is that the goal of the attacker here?
That was sort of the goal of the surrogate inversion attack. The basic goal here is just, I just want to give the model data that gives me what I want. So they're not really interested in, I mean, maybe they'll take the model for themselves, but the main goal is I just want to game the model. I want to make the model give me the outcome I desire. And this is just by manipulating data. So you would think, it's not the most sophisticated type of attack, but it can be a pretty powerful attack. I mean, they're just changing data over and over and over and over, sending it to the prediction API, getting something back, and seeing if the outcome changed for them. That's what's happening with this type of attack. It's not as sophisticated, I think, as the other ones.
Okay.
It's not as orchestrated, I guess you can say. There's really one simple step. And
so would the practical situation be something like, I'm just trying to understand what's my FICO cutoff for credit approval, and I'm going to try 680, 670, 550, 540, and then I figure out like, keeping all the other parameters the same, if my FICO score goes above 570, then I'll get an approval. Yeah. So is that something I'm trying to understand?
Yeah, essentially, yes. So you can start off with saying, well, in this case, the FICO one might be tricky because they'll just look it up and then say, no. But most of the time, they can't just rely on FICO scores. That's usually not a good practice, I think, to just rely on FICO scores. There's various other combinations. So they can give
an example.
FICO. Yeah. Of course. But yeah, in this case, yes, if the FICO was something they took from US Truth, yes, you would just keep manipulating it until you got your outcome. And then there might be a certain point where it doesn't matter how you manipulate it, it doesn't change your outcome. So that tells you change something else. So then you start changing something else. And then you keep doing this until the outcomes change for you. And once you know that, you've done an adversarial attack essentially, and you figured out how to get, in this case, you figured out how to get some type of loan or credit increase or credit card or something like that.
Cool, thank you.
And then, of course, the defenses here is sort of anomaly detection and authentication. So with the anomaly detection, you're sort of looking at the types of input data that are coming in, and of course, you're basically trying to see how different they are, or how similar they are, or how random they look. Does the make sense? Is this something you've seen in training time, or when you did validation? So this is where the anomaly detection comes in. Of course, the human in the loop is still involved. And of course, with the authentication, less of a human in the loop. It's more just about basic cybersecurity. And then, of course, you want to ensure that the authentication you have is probably the most sophisticated as possible. The third one here is called, it's called benchmark models. So basically, the idea here is if you deploy some complex model for some reason, you always want to compare it to, say, a sort of a linear model's prediction. And then the idea here is if the two models' predictions diverge significantly, then there is a chance to review the prediction, before you issue it. Since with a complex model, it might be hard to decipher what actually happened. Where with a linear model or a very interpretable model, you can decipher pretty easily what happened. And then you can compare the predictions. And then, yes, if they diverge, then there's something going on internally of the complex model or with the data input itself. So that's, the benchmark models. And you also have the fair or private models, again, that I showed in slide 6. Then you have the throttling, which is the slowing of the prediction time to give you a chance to investigate. The other common one is model monitoring. So you want to basically ensure that there's no strange prediction behavior happening in the model monitoring itself. And then, of course, there's some white hat exercises you can do. So there's on the bottom, you see white hat surrogate models, which I explained before. And there's also another concept of white hat sensitivity models. We basically try to trick your model using sensitivity analysis. And sensitivity analysis is a very common technique found in other fields of engineering, but it's also applied here. You're just sort of tweaking this model until you get the outcome you desire. And then from there, you can sort of put in some safeguards for this type of input. Because, for example, one thing that could have happened with the white hat, sensitivity analysis exercise is you sent some data that doesn't really make sense to what you understand the data to be. So, in most data science exercises, you really understand your data. So you should understand what makes sense, what doesn't make sense. Does it, those two things are something any data scientist should understand, because otherwise, you shouldn't be working on this use case if you don't really understand your data, which will go hand in hand with this type of analysis. So this last one that I will go over is called an impersonation attack. And the idea here is through surrogate model inversion or adversarial examples, they learn the attributes favored by your model and then they impersonate them. So this is basically similar to what I was mentioning earlier. With adversarials and inversion, they figure out what is favorable to them and they just mimic that, and then they get the outcome they desire. So here you can see it's like the hacker sort of peeking over at the row. In this case, you can think of it as a type of person that was sort of not denied by something, and then they're basically changing their inputs to match that, and then get the favorable outcome that they desire. And then once again, the same two things apply: authentication, disparate impact analysis, and then you also want to look at model monitoring. So in this case, you want to look for when there's a lot of similar predictions in real time. And you also want to look for input data that's very, very similar each time. So this would be kind of odd to see if you sort of see the same row appearing over and over and over again, or several times in different places, which is maybe something that a hacker might try to do. They won't just send, data all at once, they'll spread it out. So this is something to look into, is you're kind of comparing input rows to each other to see if there's not too much similarity. And of course, if there's too much similarity, that would most likely lead to similar predictions. And then that's something to investigate from a model monitoring standpoint. And from a model monitoring standpoint, there's always a human in the loop. So this is just sort of another metric to sort of keep track of. And I think keeping track of other metrics and having a human in the loop is already a concept in model monitoring. So it'll be no different to add something else to take care of. So we've gone over the several type of attacks, and then now I just want to summarize some general concerns. And the first one is using black box models. So over time, a hacker can technically, or there's a chance that they can learn more about the model than because they will just keep attacking it, and then they'll sort of figure out everything the black box model is doing. And that's not a good situation to be in. So when it comes to black box models, you really, really want to consider why you want this model to be in production, and can you use something more interpretable, which will help in many aspects of security, and it'll also help in many aspects of just understanding your model, so you can improve upon it, as the lineage of your data science use case changes over time. Another one is sort of black hat explainable AI. So explainable AI can, sort of enable you to learn about your model and what your model is doing. It can help with regulatory compliance in certain cases. and it sort of appeals to automated decision, but it can also make ML hacks pretty easy, because in this way, people are also using those types of information to learn what the model is doing, and this can be sort of damaging sometimes. So it's something to consider as well. And then the other concept here is a DDoS attack, which is just basically, what I talked about earlier with lack of authentication. Someone can keep hitting your API to get the predictions, and doing inversion attacks, remaking the training data, et cetera. So that's something to consider as well. You also have distributed. So anytime you're dealing with distributed systems and models, what you've done is basically the attack surface for the hacker has sort of spread out, and it's become very complex to keep track of. So in those situations, there's many security things to consider as well. And also the last one is sort of package dependency. So a lot of times when people build machine learning models nowadays, they're using some type of open source library. Most of the time, I don't think they're making something from scratch internally. There are companies who do that, but most of the time I think they're using packages. And then you want to see, you kind of want to analyze this package for security vulnerabilities and things like that, because you obviously don't have too much control of what they're doing. But if they're open source, obviously you do, because you can take a copy of it and change it for yourself. So this is one thing to consider as well. Anytime you're using third-party packages, you want to ensure that there's no security issues. And a lot of times if you're in the realm of, say, building data science products, the product itself will go through a security analysis anyways, whether it be by you or whoever you're selling the product to, because people already have these concerns, in mind. So I mentioned some concerns, and here are some general solutions. So I mentioned, sort of authentication and throttling for any of your prediction APIs or model endpoints. There's a concept of benchmark models. So you want to compare your complex model to something, less complex, and it's hopefully going to be less hackable. And then, for sort of traditional low signal to noise data mining problems, prediction shouldn't be that different between the complex and the interpretable model. If they are very different from each other, then you sort of want to investigate why. But I think for the most part, they shouldn't be that different. And then you would want to pick the simpler model in that case. And if you really want the black box model, you should really consider why. Why do you need the black box model? Because it's not really just about the predictions. You sort of want to understand what your model's doing for any type of future, analysis you're going to do when it's in, production. And then the next one is sort of encryption, differential privacy. Just want to make sure that the data that you have is protected, and the models are not susceptible to attacks like surrogate inversion or the member inference, which can recreate data. So that's one thing to consider there as well. And then once again, there's these ideas of using interpretable fair or private models, which sort of ties back to benchmark models. So these are types of models you would compare to your black box model. This is not all of them. There's many kinds. So this is something to consider as well. I'd really like to point out the importance of benchmark models and interpretable models. Those should be sort of the first step in a data science pipeline. Try to build something simple, evaluate it on validation, cross-validation, see how good the results are. And then you can start making other models that are maybe more black box, and then see, how different the performance is. I would stress that you should try to stick to interpretable models as much as possible, only because it'll just make your life easier down the road when it comes to monitoring, or if, say, a stakeholder has questions about what the model is doing. If you yourself can't explain the model, then the model itself should not be sort of deployed on people, or observations. So that's something to consider just going forward. It's not really just a security thing, it's more of a data science practice type of thing. So now, some more solutions, you always want model documentation management and monitoring. So in data science workflow, you're going to have a lot of different predictive models. So you should have an inventory of these predictive models, their performance, what their inputs were, all these type of metrics. And then, like I mentioned before, you want to document production models in such a way that, a new employee or whoever's monitoring it outside of, you or your group can diagnose, if there's any unintended behavior happening with the model itself. Another thing is with model documentation, you want to know who trained each model and on what data and when, because the model itself is going to be trained by maybe one person, two people, three people, it could be a group of people, but you just want to know who these people are. This comes back to security. You just want to ensure that, you understand how the model was made if something goes wrong. Another thing is to monitor and investigate the inputs and predictions of deployed models, which is probably happening anyways. But just if it's not, that should be in there so you understand how the inputs and outputs are changing and if there's anything anomalous happening. The next one is sort of model debugging. So always test your models for accuracy, fairness, and privacy before deploying them, and do some white hacking exercises. So like the surrogate model inversion, applying some explainable AI techniques to see what the hackers can see. These are sort of, I guess if you have good authentication, you might think this is not necessary, but it's better to be safe than sorry and sort of have safeguards in place for this. And then, another thing is sort of system monitoring and profiling, which is most likely happening as well outside of model monitoring. People are monitoring the systems these models are deployed on. And you just want to make sure that there's nothing odd happening in that point as well, just from a CPU, system standpoint. And then, you want to look at the number of predictions that are happening, the latency, CPU memory, disk loads, et cetera. And you just want to look for anomalous behavior as well. So in summary, ML hacking is still probably this rare and exotic thing, but new techniques coming out can sort of make this easier and more damaging. You should be aware of insider threats. So in the beginning, I mentioned data poisoning. That's sort of an inside thing. It's not really someone. It's not a third party implementing anything. Having obviously, once again, I mentioned type of authentication. Sort of a security nightmare. You should also consider that your competitors could be gaming or stealing your public predictive models. So you want to make sure you have the right type of license agreements, terms of service, and just make sure you have everything in place from a legal standpoint of view. And obviously just good old best practices around IT security, model management, model monitoring are pretty good defenses against a lot of these things. And with that said, I am done. And here are some references. The first two are a couple of O'Reilly articles, and the last one is the latest book Patrick, myself, and Benjamin Cox from H2O wrote. And there's a section on secure machine learning that I've highlighted there that you can take a look at that covers these topics in a little bit more detail.
Oh, thank you so much, Navdeep. This is an excellent overview of kind of the hop on, hop off tour of machine learning security. So this is really nice. I think we are a little bit over time, so I don't know if we can have like a formal Q&A. I just want to bring up one thing which I'm struggling with personally, and we'll kind of just have it as an open question, or maybe pick up the discussion offline. It's going to be complicated, at least the companies I work with, to basically incorporate all these aspects as part of their workflow, because these are very novel concepts. And the way, and we do a lot of education, right? So when we interact with our customers, they're still going through this process of understanding what machine learning is. and what machine learning models are, what complexities you need to think about. And incorporating all these things, becomes a challenge of defining what's good enough, right? So what's good enough in terms, the way I kind of position it from a framework perspective is, one, there is the assessment, know what you're having, and kind of understand what you have in terms of problems, in terms of opportunities for improvement, loopholes, where the challenges are, etc. Right? And then you put in your mitigation and controls, wherein it could be guardrails, it could be fixing the problem, it could be human in the loop, whatever it is. And then you have the residual risk, wherein you haven't been able to address and you're thinking about either to transfer it or put in additional guardrails or whatever it is. But then comes this layer of auditing, wherein we have done things which we think are good enough. Now, can a qualified company or an external agency come in and look at whether we are, blind to certain spots which we may not have looked at, right? So, look for those blind spots, look for those things which we think are okay, but someone may say, hey, it's not good enough because you may be dealing with these challenges and you may have to encounter it. And then the unknown unknowns, wherein you may not even have thought about it, but someone would come in and say, hey, this is something you haven't even thought about, and you got to think about it, right? So where do you see the spectrum kind of evolving? Because it's not going to be feasible for every company to have all the 360-degree expertise in-house, explainability expertise, model building expertise, MLOps expertise, security expertise. And what's the role of an external auditor, maybe a specialized auditor, who could potentially help out either in a postmortem scenario wherein something bad has happened and you've got to fix things, or a proactive scenario wherein you're actively ensuring that you are knowing what you're doing and trying to fix the potential loop.
Yeah, I think all these different aspects, yes, I agree that they're very involved. There's a lot of things to the pipeline, et cetera. I think one thing to consider first is once you really understand the use case, I think you'll figure out what aspects are most important to you. Because it's one thing to say I need everything, but maybe in reality you only need a subset, which I think is usually the case. Sometimes you just need a subset of things. So for example, if someone's starting out with just machine learning, then there's no point of considering security yet. You're not even close to deploying anything, so you shouldn't have to worry about it. Explainability, you'll get to that point eventually once you learn how to make the machine learning model itself. Everything's going to start with the data and the use case. Once you have that, everything I think will start to fall into place to a certain degree, because you'll know what you're looking for in the model itself. So I know I stressed explainability, but there could be people out there that really don't care about explainability. It's possible. So for them, they might just skip that whole section. And of course, this once again comes back to the use case. Once you've sort of understood the use case and what type of information you want to convey to people, then you know what you need. In terms of security, specifically, I think that also depends on the use case itself. You sort of have to think to yourself, how valuable, is my use case to someone outside of the company. So if you're in, financial services or some type of financial institution, you're very valuable to a lot of people outside of the company. And if you're building some model to figure out ad placement, I don't think you're that valuable to someone outside of the company. That's not to say you shouldn't have security. I just think that's to say the degree of security is different. So a lot of times, with those companies that aren't in financial services or anything, authentication might be good enough to sort of get things going. But then, the bigger institutions who have the resources, they will implement these things. So for the bigger financial institutions, for example, they already understand a lot of the initial concepts before security. And then they have people who understand model monitoring. So then security kind of combines the two, where you're taking different techniques you've learned from explainability, like disparate impact analysis. You know about building machine learning models, so surrogate models are no different. You sort of know these concepts, and then you combine it with the engineering, authentication, and the throttling of the prediction times, et cetera. Combining those will allow those institutions to implement security as well. But yeah, I think all of this always comes back to the use case. Once you truly understand what your goal is, then all of these technicalities will start to fall into place. And it also depends on the level you are as a company when it comes to machine learning. There's companies still who are just starting out. They haven't really done much in terms of machine learning. They've probably done a lot of analytics, pre-model building stuff. But now they're venturing off into machine learning. And even then they have to evaluate their use case once again, because the initial use case could have been that analytics is just enough. Dashboarding is just enough to get what I need. And now they're probably looking at some automation. And then they have to, figure out again what this automation is really doing.
Absolutely. Cool.
Yeah.
Thank you so much again, Navdeep. This was an excellent session. And for people who are interested in these topics, please don't forget to sign up for the Quant University Summer School mailing list. You will get invites to the future sessions. Next week, we have Matthew Stewart from Harvard University, who's going to be talking about covariate shifts and data shifts. And we'll talk about aspects of monitoring which needs to be thought about when you're building the machine learning process. So thanks again for spending your lunch break or your morning coffee with us, depending on where you are. And we will see you soon. Thanks again, Navdeep. Take care.
Thanks.
Bye.
Thanks, everyone. Bye.